There we go. Hi. So the second one I wanted to do for video was the problem 19. We're dealing a lot with pregnancy this week, gestation. And what we see is that the population mean is 266 days and the standard deviation is 16 days. So the first thing that Sullivan asks is, what is the likelihood that a single pregnancy lasts less than 260 days? So here we have a sample. In this case, this is actually not a sample mean. It would just be actually x sub I. And so you could just call it x sub I minus mu. How likely is it that one pregnancy, x sub I, would be 6 days or more away? And it's our calculation to do it for a single one is simply to take the difference between the observation minus the population mean and divide it by the standard deviation of the population. And in this case, then that becomes, oh, I just get this announcement that Jessica Simpson is pregnant. I don't even know who she's dating. Okay, so that becomes then 260 minus 266 divided by 16. That's a negative 6 divided by 16. And then if you look, that is basically our z-score. And if we look at where the z is at 0.375, or I'm sorry, we just actually take that likelihood right there, which is 0.375 or 3/8 at that point. And so then if we come, what we do, that's our z-score. So we take the 0.38, which is what Sullivan rounds up to, and we look to the far left column in the z-table in Table 5 in Sullivan. And what we see is first we go to the z equals negative 0.3, which is on the far left of that column. And then we travel over to the 8th column to negative 3.8. The column heading is 0.08. At that point, the value is 0.352. That's the proportion of the normal curve or the normal distribution that is to the left of 260. In other words, if the normal distribution is centered on 266, and we're at 260, we want to know what percentage of bursts do we expect to take place at 260 days or less, and that would be 0.352 is the proportion of bursts that, did I just say deaths? That's the proportion of bursts that would take place at 260 days or less of gestation. And so, as I just talked about that, and so 0.352 implies that the likelihood of a single pregnancy being 260 days or less is 35. If we multiply the 0.352 by 100, we get 35.2%. Now, notice it's not the likelihood of an exact observation. We're saying that it would be this much or less. The likelihood of any single observation is infinitesimal. So we generally don't speak in terms of those. Part B of problem 19 says if we have a sample of 20 pregnancies and the sampling distribution of the sample would then approximate the t-distribution, but actually Sullivan goes ahead and uses the normal curve already at 20. We'll go with Sullivan and not with Beamer on this, since it's what will give you the book's correct answer. They treat this as normal. And so what we want to know is the likelihood of finding a sample mean of 260 or less, given that we have a sample size of 20. What we do here then is we have mu minus x bar for the sample size 20. This is a bit messy, divided by the standard deviation over the square root of 20. And so that gives us 266. 16 divided by the square root of 20 is 3.57. The square root of 20 would be somewhere a little bit more than 4 and less than 5. So this looks reasonable. And that gives us a z-score of 1.68. What we see from that is that we have a 0.0465. And here, again, if we go in Table 5 to the far left, this is I'm sorry. So this is an arrow, by the way, and it's not an equal sign, and I'll get back to that. So our z-score is 1.68. If we go to table 5 and you go to the far left to z equals negative 1.6, and then we go down over 8 columns to 0.08, the entry is 0.0465 or 4.65%. So the likelihood that a sample of 20 would have a mean of less than of 260 or less is 4.65%. Now this is worth sort of just a moment to compare A to B, which is comparing A to B. We see that for A, the likelihood of any single birth being or any single gestation period being less than 260 is 35.2%. The likelihood that the mean of a sample of 20, that the likelihood of 20 pregnancies having a sample mean of 260 or less is only 4.65%. And this is sort of, when we talk about the power of large numbers or the central limit theorem, this shows us why the power of the central limit theorem. One observation, we have a 35% chance of observing a gestation below 260. 20 observations, we have a 4.7% chance of observing a sample mean of less than 260. Imagine if we went to 400 and so forth, which actually we're going to sort of implicitly do right here, which is now, and this is the key change, the numerator stays the same, but the 16 is divided by the square root of 50 now, which is the square root of n, and that is the 16 divided by 7.07, so we get negative 6 divided by 2.26, and that is our negative 2.65. When z equals negative 2.65, the probability that x is less than 260, again, here we go to negative 2.6, we go out 5 columns, and we see that it's 0.004. I just multiplied by 100 rather quickly, so that it's 0.4% likely. So we want to just sort of understand that. So we went from a 35% chance that any one pregnancy would be less than 260 to a 4.7% likelihood that the mean of 20 pregnancies would be less than 260 days, and to a likelihood of 0.4% that a sample of 50 pregnancies would have a mean of less than 260 days. So I hope that's helpful, and we will discuss the last part.